Hi, this is Connor Earl, and we're going to be talking today about our process control project, which was controlling the blood oxygen level for babies in the newborn ICU. The inspiration for this project came when I was shadowing my nurse, or my sister-in-law, who's a nurse in the newborn ICU, and I watched all day as she adjusted a valve to to increase the saturated oxygen level for these babies in the NICU, and it was really important that that level stayed within a certain range, because too little and the babies don't get enough oxygen, too much and they actually can have some developmental problems, especially with their eyesight. So our dynamic control system was essentially, our process variable was our saturated blood oxygen level, SpO2. Our input variable was our oxygen fraction in the air that we're adding to the incubator. And a disturbance that we accounted for was the heart rate of the baby. So here is obviously a very sophisticated model of our system, a representation. As you can see, we're controlling the amount of oxygen entering the incubator with a valve and measuring our process variable with a simple infrared sensor. Now, let's talk about our dynamic equations. We first did a mole balance on the incubator, and as you can see, this top equation is just that. We simplified that equation by assuming the molar flow rate in is the same as the molar flow rate out, and further simplified it here to get what is essentially a first order plus dead time model, where our tau was about 1 minute. Now here was a little more complicated. We needed to take a steady state variable and make it a dynamic variable. So that's what this first equation is, where we have our SpO2 within the baby changing with time with a certain tau of about 5 minutes. And we added in this red here, the disturbance of the heart rate. This equation is an equation we got from the literature. It's essentially how the oxygen from the air gets into the lungs, and how that then affects the SpO2 level, so the saturated oxygen in the blood. And we adjusted these parameters to match some data that we were able to obtain from a real-life case of a baby suffering from respiratory distress. So as you can see, this shows a simple doublet test where we decreased and increased the oxygen level, and the FiO2, the red line, is what the baby is actually breathing, and the YO2 is what we're adjusting. And this black line here is the actual oxygen concentration in the blood, which actually is really low in this case. We need it to be at least above 90%. We then took that data and did an FOPDT optimization to obtain some tuning parameters, which we then fed into our PID controller. And I'd like to show you a quick animation of what that ended up looking like with our PI controller. So as you can see here, we got our code. We have some of our tuning parameters, and we'll go ahead and run this. And what we're looking at is a baby that starts initially, if we're walking this black line, initially at respiratory distress. Their SpO2 is below the healthy level. We adjust that by increasing the amount of oxygen that we're flowing into the incubator, the concentration. Now when we reach that set point, what we see down here on the bottom is heart rate data, and this is actually real heart rate data taken from a real patient, and how that heart rate actually ends up affecting our SpO2 level. As the heart rate decreases, not as much oxygen is getting to the tissues, and so we need to increase our input variable, the YO2, to then increase the fraction of inspired oxygen, FiO2 for the baby, so that we can maintain that sweet spot. You can see this baby was having a hard time this day. Their heart rate was up and down, and it really affected their SpO2, but as we can see, by implementing this controller, we're able to keep their oxygen level within their blood within a healthy range for most of the time, which was a success to see. So in conclusion, take you back to the PowerPoint, we were able to show that our PI controller could control the SpO2 level in a newborn infant, and we did that with some moderate success. Ride or die.